So I mentioned alpha is the probability of a false positive result. And I mentioned that the most common value for alpha is 0.05, which represents a 5% chance of a false positive result, or a 5% chance of rejecting the true null hypothesis. That's equivalent to a false positive result. Because if the null hypothesis is true and you reject it, that's a mistake. Now, this 5% isn't the only option. However, people think that that's a rule that you have to do it. There's a lot of things, heuristics, as we call them, in this world where people just accept them as if they were true, even though they are not. But people like simplicity, right? Other options that are available are 0.10 and 0.15. 0.15 is much less likely to be accepted by a reviewer if you are submitting something for publication, but it can be. I mean, I've used both of them, and even in grant applications, I've gone up to 0.15, but those are best for the initial testing stages, like you're trying something new that you're interested in, like for instance, some new program that tests a new program to help increase, I don't know, job performance or something like that, or when your sample size is really, really small. This power, as I mentioned before, is dictated to a large extent by sample size. And there's nothing bad, nothing at stake, nothing important at stake. Like for instance, if you're testing a drug, and a drug could have some dangerous side effects, you don't want to have a 15% chance of a false positive result because somebody could die if the drug is dangerous. We can also reduce the alpha from 0.05 to 0.01, even lower sometimes. And you do in some testing situations we'll learn about later. You can reduce it to very small values. But this is when we will not accept being wrong because there's potentially negative consequences to being wrong. For instance, as I mentioned, if we're testing a drug, or if we have a very large sample size too, we tend to shrink our alpha because when we have a large sample size, everything looks significant, right? So by reducing the alpha, it makes it more difficult to commit a type 1 error. Here's an example of the relation between the z value and probability and alpha. So in this case here, our probability of a false positive result, or alpha, is 0.05. This is our population, right? So in our population, values this large or larger would occur 5% of the time or less, right? So if we say our alpha is 0.05, we'll accept the 5% chance of a false positive result. So when we're making this decision, we're saying this is the acceptable level of being wrong. If I say my alpha is 0.05, that means I'm accepting a 5% chance of being wrong. So I'm okay if I'm wrong 5%. Let me make that clear. I'm okay if I'm wrong 5% of the time. It means I'll be right 95% of the time. So I don't mind being wrong 5% of the time. You understand that? So this is my cutoff value. Anything above that is not acceptable, right? For my testing. Anything below that I would consider significant. So if I was testing some sample and I wanted to know if it differed from the population, I selected my alpha to be 0.05. That means I'm accepting a 5% chance of being wrong. 5% chance that my conclusion is wrong. Let's say I get a z value that is larger than 1.645. So remember, these z values are in standard deviations, right? So a z value of 0 means that it's right here, 0 standard deviations from the mean. A z value of 2 means it's 2 standard deviations above the mean. A z value of -2 means it's 2 standard deviations below the mean. The z value of 1.645 is 1.645 times larger, or 1.645 standard deviations away from the mean, right? So it's this far away from the mean. So any value that I calculate that would be that large or larger would have less than or equal to a 5% chance of occurring. So if I calculated something and it has a z value of 2, right, and I said that my acceptable level of a type 1 error is 5%, the z value associated with an alpha of 5% is 1.645, right? So anything larger than that value would be okay for me, because I could still be wrong, right? I could say that my sample doesn't belong to the population, and it actually does, because we can have extreme values in populations. But since that value has less than or equal to a 5% chance of occurring, I would be wrong, right? I'd be wrong, because it still does belong to this population, but it's an extreme. But I only have a 5% chance of being wrong. So I'm okay with that. So this is what you got to be thinking. Like, you got to be thinking about these different scenarios here. Okay. So we're going to use this test statistic called the Z statistic. So it looks a lot like what we used when we were calculating Z scores, so we can get percentiles, right? Except for that now we're using the standard error of the mean as their denominator, because that's the standard deviation of the sampling distribution of the mean. So let's go to our example. We have data from 33 DHS students, Danielsville High School students, who completed the RWI, and they have a mean of 70. Question is, do Danielsville High School students weigh more on average as measured by the RWI than high school students statewide? By the way, you should notice how specific this research question is. So notice how I say, do they weigh more on average as measured by the RWI? When you write these research questions, it's going to be very, very specific. If you said, do Danielsville High School students weigh more on average than high school students statewide, that wouldn't be a really good research question, because you're not specific enough. How did you measure weight? Oh, we did it using the RWI. So it's very, very precise. Our null hypothesis in words is the sample mean equals the population mean. So here our population mean is 50. Our sample mean is 70. So this is our null hypothesis. Or you could say the difference between the sample and the population mean is 0. So that's what we're assuming is true. So remember, we start with the assumption that this is true. Even though you can see it looks different, 70 is greater than 50, we have to start with the assumption that they're not different statistically. The alternative hypothesis, well, this one's easy because the sample mean, we just say the sample mean is greater than the population mean. Well, we can see 70 is greater than 50. So you're not going to write the sample mean is less than the population mean. You're just going to write the sample mean is greater than the population mean. So I'm following the steps that I outlined the other day. We're selecting our alpha. This case, we'll do 5%. So we accept no more than a 5% chance of being wrong. False positive result, type 1 error. We have the population standard deviation. Because of that, we can use this test. Now, there's times when we don't have a population standard deviation. In that case, we use something called the t-test. In the t-test, we use the sample standard deviation instead of the population standard deviation. We know from what I've discussed before, the sample standard deviation is an unbiased estimate of the population standard, or standard deviation, or you can do variance, whatever you want. Okay, so, but it's an unbiased estimate of the population standard deviation. This is called a t distribution versus what we're working with right now is a z distribution or standard normal distribution. This is a little bit different, not much, and the two become the same when the sample size gets larger, but that's just for another time. We'll be doing that soon enough. But you need to have the population standard deviation to use the z-test. Just know that. Then we determine if the test statistic value is significantly different from the population mean. That's known as statistical significance. So we ask ourselves, what is the probability of the observed result, the z-value that we calculated, or greater, given the null hypothesis is true? So again, we're assuming the null hypothesis is true. So we say, if the null hypothesis is true, what's the probability that we'll find a value this large or larger? Okay. And remembering what the null hypothesis means. So what that means, it means the sample mean is not different from the population mean. We go to the z table and we look up a value. What's the probability of our value or greater? So here we calculated our value to be 3.830 because we had 70 minus 50 is 20. We had our standard deviation is 30. So you'd have to go back to the top of the other day to see that. We had a mean of 50 and a standard deviation of 30. We had a sample size of 33. So we go ahead and do this calculation. This, by the way, is our standard error, right? This is our definition of a standard error. We do our calculation, we get 3.830. So we want to find what's the probability of value that large or larger, okay? So let's do it. So let's go to our table. And here it is. So we said 3.830. Okay. 3.830. Well, so we go to our table and our table ends at 3.5. So there is no 3.830, but this value all the way in the right-hand corner is 3.59. So we know that our probability of a value of 3.9, less than or equal to 3.9, is going to be 0.4998 plus 0.5. Because remember, you always have to add that 0.5, that 50% here. So we want to find out what's the probability of this area here. What we get in this table is the probability going up to 3.59. So that's where Z is. We're interested in what's the probability beyond that, right? Okay, so it's going to be smaller than whatever this is, right? 1 minus 0.9998, right? It's going to be smaller than whatever that is, right? So that's what I did here, right? Well, it's going to be somewhere less than 0.0002. It's going to be really, really small. Okay, it's going to be really, really small. So this kind of gives us an indicator that this value is really, really small. The sample mean, the probability of a sample mean that large or larger, right, 70 or larger, which translates to this Z value of 3.830, is very, very small. That means if the null hypothesis is true, right, probability of observing a value 3.830 or greater is somewhere less than 0.0002, right? Or if you multiply that by 100, it's 0.02%, right? It's very, very unlikely to occur. Now, it still could be a part of our population. It could be some outlier. And if I conclude that this sample does not belong to my population, I'd be wrong, but my probability of being wrong is 0.0002, and I can live with that. I mean, I'm fine with that, no problem at all. Okay. Often when we're doing these tests, we're not looking at probabilities because we calculated a Z value. And once you start getting to know the common Z values, right, you can just use them. And you can make a direct comparison between your calculated Z value and what is known as a critical value, right? A critical value. You can just make a comparison. The Z value that's associated with an alpha of 0.05, now some of you might think, well, wait a minute, didn't we do 1.96 the other day? Let's not worry about that now. The last lecture before your exam, we're going to talk about 1 versus 2 tail test, but we're not doing that today, okay? The Z value associated with a critical value of 0.05 in the scenario that we have is 1.645. And we know our calculated value is 3.883. Where's that figure? Here it is. Yeah, 3.883. So that value is further and further away from the mean. It's pretty much close to 4, right? 4 standard deviations for a mean. So that's really, really far away from our population mean. We use our population mean to be the indicator of the population because that's the expected value of the population. So if our sample belonged to the population, its mean shouldn't be that far away from 0. But our mean when we translated it into a z-score, right? We took 70 minus 50 divided by the standard error, was all the way out here. So the probability of our sample is very small. Well, we can do a direct comparison between our z value of 3.883 and 1.645. Since our z value is way further than this cutoff point, and remember, this cutoff point represents the upper 5% of the population, we know that we have a statistically significant difference. So I can just judge significance by comparing my value to the critical value. If my value, calculated value, is greater than the critical value, I have statistical significance. I can also compare the probability of my observed result or greater to my alpha. So there's two different ways I can judge significance, statistical significance. I tend to want you to write down the rules so that you don't forget them. They need to be ingrained in your head, okay? What else? I talked about that. So we draw our conclusion. Oh, so the question, is the sample, the mean RWI of 70, significantly different from our population? Oh, I love all this stuff. So if we say, yes, it is, which we ended up doing, we can still be wrong, but the probability of us being wrong is very, very small. You understand this now? Because our p-value represents the probability of our observed result or greater, given the null hypothesis is true. So that means we're saying, what's the probability that this sample mean belongs to our population? And the probability is 0.0002 multiplied by 100. We have the probability of a value that large or larger is only 0.02%. That's tiny. Since we set our alpha at 0.05, we don't mind being wrong 0.02% of the time, because that's so improbable. In fact, we say, hey, we're okay if we're wrong 5% of the time. Okay? That's how we do that. Okay. All right, guys. So I already covered all of this, but here's a little example I give to understand what rejecting the null hypothesis means. Okay, and I just mentioned that an alpha of 5% means that we accept being wrong 5% of the time. So where's my little example? Ah, here it is. I try to be creative in these. Imagine that you meet someone who is so cool that you believe this person is otherworldly or comes from another planet. Individuals like her can be found in our population, but it's very, very unlikely. The question is she from a different world? Or is she just a rare but extremely cool member of our population? Think about your coolest friend. Wow, is this person actually real? Imagine that the probability that someone like your new friend can be found in our population. The probability is about 0.001 or 0.1%. That's the probability of finding somebody as cool as her in our population. This also means that the probability that she doesn't belong to our population is the complement of that, right? 1 minus the probability that she belongs. So there's a 99.9% chance that she doesn't belong to our population. Right? So if you conclude she does not belong to our population, but she actually does, you'd be wrong. But the probability of you being wrong is only 0.001. Given that you decided you're okay with a 5% chance of being wrong, you are okay with this. You're okay with being wrong at this level. Okay? So you can say she's from another planet. Wow, this person's so cool. She's otherworldly, man. You're okay with that, all right? The last step, of course, we're going to repeat our findings, our study, to see if our findings are valid. We need replication to ensure validity. All right. Now let's do a practice problem. So I'm going to go scroll back and forth between a couple pictures. So we have data on 25 Pipersville High School students who completed the RWI. Their mean was 55. Our research question is, do these students from my Pipersville High School weigh more on average as measured by the RWI than high school students statewide? So our population mean is 50 and our standard deviation is 30. So let's go through all the steps. First, we'll write out the null and the alternative hypothesis. So here we are. Here's the problem. So we have our mean is 55. We have 25 as our sample size. Population mean is 50. The standard deviation is 30. So we write down our null and our alternative hypothesis. The sample mean is equal to the population mean. The sample mean is greater than the population mean. That's our alternative hypothesis. So our null is that they're equal. Our alternative is that they are not equal. We calculated our Z value. Well, actually, so we started with our alpha, right? Our alpha was 0.10. So with an alpha of 0.10, we go ahead and identify our critical value. So in this case, we have an alpha of 0.10. We use this little equation to calculate our critical value. So it's Z1 minus alpha divided by 2, which is Z1 minus 0.10 divided by 2, which is Z1 minus 0.05, right? Which is Z of 0.95. And remember, the 0.95 is a probability of a Z value, right? This large. So this is actually basically the percentile. So it's the probability that one is less than or equal to Z, whatever the Z score is. So that probability is 0.95. So we want to find a Z statistic, the critical value associated with this Z value. And then if we go to our table, so we look for 0.95, and don't forget, we only get the value between 0 and Z, whatever that Z value is. So we have to add 0.5 to this. So if we want 0.95, it's going to be 0.95 minus this 50%, because we're only getting this amount right here. So that's 0.45. So we go to our table and look for 0.45. And it's, as you recall, it's between 0.4495 and 0.4505. So there's no 0.45. So because of this, I chose 1.6 and 1.6. So here it is, 1.64. Well, it's between 1.64 and 1.65. So I just chose 1.645. I split the difference, right? So we go back to our picture, and I chose a Z of 1.645. Next thing we do is calculate our Z value. So we have 55 minus 50 divided by the standard error, and that's your standard deviation divided by the square root of your sample size. That's 5 divided by this rate, this quotient here. We get 0.8333. So it's already smaller than 1. So that's giving me a lot of information. It means it's not horribly far away from the mean, right? It's not even 1 standard deviation above the mean. With 1 standard deviation, you have a value 1 there, but this is less than 1. So to judge statistical significance, we compare our value to our critical value, right? So our critical value is 1.645. So this value is lower than 1.645. Let's go back to this picture here. So right here. So here's the Z value of 1.645. To be statistically significant, we'd want it to be further away. That means it would have a smaller probability of occurring given the null hypothesis is true. So this is our null distribution, or null hypothesis distribution. So the value is somewhere in here, right? Like right here or something. So it's not that far away from the mean. So it has a high probability of occurring, certainly a higher probability than we would have thought. So let's keep on going. All right, so So we need to find what the probability of a value Well, so we can reject the null hypothesis just by using this criterion right here, right? Remember, I just mentioned that there's two different ways to reject the null. One is to compare it directly to the critical value, and it to be significant, it really needs to be greater than or equal to that value. Some people will say greater than or equal is fine for me. Some people will say if your actual critical value is exactly the same as your calculated value, they would consider that marginally significant. Yeah, it's kind of stupid, to be honest. So I'd say greater than or equal to 1.645 would be considered significant. But this definitely isn't, so we can conclude that since this value is less than our critical value, we fail to reject the null hypothesis. So that's one way to do it. The second thing we can do, of course, is to calculate the p-value. So the p-value is the probability of having a value this large or larger, 0.8333 or larger, right? So we want to see what's the probability of a z value that's greater than or equal to 0.8333. So that's 1 minus, well, again, we have to go to our table. It's at 0.833. So this is 0.8, 0.80, 0.81, 0.82, 0.83. So we get 0.2967. So this is the probability of a value between 0 and 0.833, right? So there's only about a 30% difference between the mean and this value. But don't forget, we have to add the bottom portion over here, right? So the probability of being less than or equal to a z value of 0.833 is 0.2967 plus 0.5, right? So that's what we have here, right? 0.5 plus 0.2967, so it's 1 minus 0.7967 or 0.2033, and since 0.2033 is greater than 0.10, so we fail to reject the null hypothesis. So this means that a z value of 0.833 or larger has a 20.33% chance of occurring if the null hypothesis is true. So in this case, we would also fail to reject the null. So we can use two different approaches to rejecting the null, either using the critical value criterion or the alpha criterion. Okay, let's see what's next. All right. The next question was to calculate a confidence interval, but this question was a 95%. See, I switched around there, right? For doing a statistical test, we used an alpha of 0.10. But to do a confidence interval, I'm switching it down to a 95% confidence interval. So you just got to be able to play with all these values. Okay. All right. So the equation for a confidence interval is the mean plus or minus this margin of error. The margin of error is whatever this z critical value is. And again, we have to divide by 2 because remember the confidence interval surrounds the mean. So it's both above and below. One portion is below the mean, one portion is above it, times the standard error of the mean. So we're doing a 95% confidence interval. With 95% confidence, there's a 5% chance of a false positive result. So our alpha is 0.05. And we just follow the same process. We know our standard error is 6 from what we did before in our calculation. Now, I told you before, when you're doing a 95% confidence interval, you might as well just remember this value. It's 1.96 for the confidence interval. We'll do this later when we're talking difference between 2 and 1 tail test, but that's not where we are right now. So it's 55 plus or minus the margin of error. So with our margin of error, our 95% confidence intervals, remember it's 55 minus 11.76 is 43.24. And then we have 55 plus 11.76 and we get 66.76. So that completes the problem. All right, everybody, thank you very much. I hope you enjoyed this as much as I enjoy. I always enjoy doing this. I mean, it is never a dull moment. I'll tell you, never a dull moment. Thank you.